study one of them.
I didn't study
Well, I'm going to study right now.
Periodic table.
And we're live. All right, let's do this. So, number 3, the proof. Here we go. Welcome to the Thunderdome, Internet. Everyone is sick here, including myself.
I'm not sick. I'm not sick.
Bailey isn't sick, but her leg's broken. So.
I'm not sick. Joel's working.
All right, so. Wow. Do it. Thanks for waiting until we started.
Yeah.
BCF is this angle right here. And DCE is this angle right here. So we got some overlap. What? Everyone reacts that way to overlap. It says C is the midpoint of BD. Well, if that's true, then it divides BD into 2 equal pieces that are congruent. And it tells you CE is congruent to CF.
I'm even wearing my glasses and I still can't see it.
Wow. But at least you're not sick. All right, so our job is to prove ABD isosceles, which is the big triangle. Remember, to be isosceles, you have to fit the definition of isosceles, which is that it has 2 congruent sides. So here's my game plan. I'm going to try and prove these 2 triangles congruent, the little ones at the bottom. And the reason for that is because if I know these are congruent, then I know their angles are congruent, including these 2. And if those 2 angles are congruent, then by the converse of the isosceles triangle theorem, then I know these sides are the same. And if those sides are the same, then it fits the definition, right? So, step 1, get as much information as possible about these triangles. Step 2, prove them congruent. Step 3, use their parts to say that these guys are congruent. And call it a day. All right, so don't write this, just watch, because literally you don't have to write it. We're going to skip all these steps and zoom through it. We did this last semester. I would like to have you guys not have to write as much this semester since we proved a lot of stuff. And now we can take it for granted. All right, so this blue angle right here is angle BCF. And it is made up of 2 other angles. What 2 other angles is BCF made up of? ECF, which is this angle. I'm going to make that angle green. So I'm going to write ECF. And what's the other angle it's made up of? ECB. Right. I'll make that orange. Now remember, color means that they're congruent. So when I write angle DCE, the other blue angle, that means it's congruent to BCF, right? And that was given to us. And DCE is made up of 2 angles as well. Well, first of all, it's made up of that same green angle, ECF, right, that overlap. And it's made up of another angle, which I'm not going to color orange because, again, we don't know that those 2 angles are congruent. So I'm going to color it a different color. Spoilers, it will be congruent. I'll be pink. And what's the name of that pink angle? FCD. Very good. Cool. So, how did I know I was allowed to do that? By angle addition postulate, right? The 2 little angles make up the big angle. The 2 little angles make up the big angle. That's kosher, okay? We're not going to write that. We're going to skip a bunch of steps. But that's the idea behind it. So now, if these guys both equal blue, and these guys equal blue, don't they equal each other? This should equal that, right? Does that make sense? If this equals blue, and that equals blue, then this equals that, right? Another way of saying it could be like 3 plus 2 is 5, and then maybe like 4 plus 1 is 5, right? If they both equal 5, then they must equal each other, right? So, I'm going to write that out. You're not going to write it. Don't do it. Because you won't need to write it for the proof. I'm just showing you where my logic is coming from, and then we're never going to have to write stuff like this again. So, ECF, FC. Cool? So we did that by substitution, right? We switched out this bit right here for this bit, right? We put it in there because we know that it's equal to blue if they're both equal to blue, then it's equal to blue, right? So put that there, and now it's equal to this. Are we cool with that concept? I think words are hard, but math is easy. Do we see the logic behind this? I'm not doing very good at saying, good job of saying the words. But do you see how I got there? Bailey?
Sure.
This equals blue, and that equals blue. Blue means they're both the same, right?
Wait, how do we know they're both the same?
That was given to us.
Oh.
That's why I did them the same color. So DCF and DCU are the exact same thing. So if this equals blue and that equals blue, then they must equal each other. Okay? All right, so I wrote that. And now you'll see if I do subtraction of both sides, I can subtract DCF from both sides because they're the same thing, right? And when I subtract it from this side, it goes away, and I'm left with this, which must be a true statement. So now I know that the orange angle and the pink angle are the same. Do you follow my logic? Okay. So I'm going to write none of this in my proof, but that's the idea. How did I accomplish that? Angle addition postulate, substitution, and then subtraction, right? I'm just going to call it angle addition postulate. So when I write my proof, I'm going to say phi angle addition postulate. And then I'm going to jump to the chase. I know that ECB is congruent to FCB. Cool? So when you have overlap, like we do here, with the two blue angles, you can subtract the overlap, and what's left over must be the same. Does that make sense? I have two equal angles overlapping, right, the two blue ones. And if I subtract their overlap, what is left over must be the same. We cool with that? Right. So that's my angle addition postulate. So now I know those two angles are the same. And since they're now the same, I'm going to use the same color. I'm going to color them in black. You don't have to. I just want you to remember that those are in fact the same. Okay? Now, my goal was to prove these two triangles congruent. That way I can say their angles are congruent here and here, which means we have opposite sides congruent of this triangle, which means it's isosceles. So, do I have enough information to prove these two triangles congruent? This triangle and this triangle? Yes, I do. How do I know they're congruent? Side, angle, side, right? So I'm going to say by side, angle, side. Those two triangles are congruent. Maroon, burgundy, chartreuse. Triangle, I'm going to call it BCE for the left one. And the one on the right, well, angle B is made up of the unknown side and the pink side. Unknown side and pink side over here is angle D, so they must go together. C is made up of green and pink, so green and pink is also C on this side, so C goes with itself. And then E is unknown and green is F. So that one's not too bad. Everybody cool with that? All right, cool. So now that those triangles are congruent, we know their parts are congruent, right? Most importantly, these parts. How do I know those parts are congruent? Because look, angle B and angle D are in the same corresponding position, right? So we say by corresponding congruent to parts CCP. I know that angle B is congruent to angle D. Cool. Right? If the triangles match up, then their parts must match up. Which parts? Well, the ones that are in the same spot. That's why we spend so much time to make sure those letters are correct in the right order. And now that I have these two angles good to go, then I know this side is congruent to that side. And I know that by the triangle, or the isosceles triangle theorem. Is it the theorem or the converse, though? Starting with the angles, we get the sides. Converse, right? By isosceles triangle theorem, THM, converse. I know that AB is congruent to AD. So those two big sides are congruent. And if we have two sides of the big triangle being congruent, doesn't that fit the definition of isosceles, right? So we're going to say by definition, that's an isosceles triangle, right? No way around it. So last but not least, by definition, triangle ABD is, in fact, isosceles. Swag box. Love the swag box. Bless you, Autumn. How does one feel? a dead cat. There we go. How do we feel about angle addition postulate with the overlap? I think that's the weirdest part of this. Does everybody see the logic here? Blue angle is made up of these pieces, blue angle is made up of these pieces, so they must equal each other. Those go away, and we're left with this. So we cancel out the overlap, and we're left with those two angles, which means they're congruent. Are we okay with that idea? Sort of? Okay. Let me highlight this blue again. So I think the trickiest part of this, which is why I want to spend some time on it, is seeing that those two blue angles overlap. And where they overlap is that green. So if I subtract the green from both the blues, right, that gets rid of this part, and it gets rid of this part. And what we're left with is just this bit and that bit, and those must be congruent. That's what's left over. It's similar to when we did segment addition postulate. Remember when we had something like this? And we would say that the overlap here, if you subtract it once, right? Then you can add this bit and this bit together, and we get the whole thing, right? So what we're doing is we're subtracting the overlap here from both of those, and what's left over is going to be congruent. So I shortcut that and just say biangle addition postulate, blah, 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 blah. The leftover pieces are congruent, okay? So this angle here and this angle here, the two leftover pieces, they will be congruent. How do we feel about this? Are we decent on that? I will in a second. Are we decent on this? Okay. After that, I think you guys feel pretty good. Side angle side, everybody cool with that? Zoom out a little bit. Side angle side, everybody cool with that? All right. CCP, the parts must be congruent. Now, I chose to talk about these specific parts because that's what I wanted, right? Everybody cool with the idea of CCP? If the triangles are congruent, the parts are congruent? Okay, grab. And then, if we have congruent angles here and here, then we have congruent sides here and here. That's what this is, triangle, isosceles triangle theorem Converse. Cool with that? Lastly, that's an isosceles triangle. Has two congruent sides. Do you feel decent on that one? I'll take decent. Let's look at number 4. Right. Very similar ideas here to the last one. So, first off, LM and LP. Stop it. LM congruent to OP. As they should be. NLO and NOL are congruent. So NLO is this angle right here. And NOL is this angle right here. What does that mean about this triangle? What does that mean? It's going to be isosceles, right? By the converse. We're going to get those sides for free. Don't do that now because that's not given to us. And we've got these guys, which are perpendicular. So ML perpendicular to LO. So here's ML. Here's LO. It's saying that's a 90-degree angle. So it's going to look kind of gross, but that's 90 degrees. Okay? So that blue angle must be less than 90, right? And it adds with whatever this angle is to make 90. We cool with that? Same thing over here. So those are both 90. They're kind of ugly, but it's okay. So we're trying to prove MN and NP together. So don't do this, but I'm going to do it. I'm coloring these in so you know which segments we're talking about. We're talking about this segment right here, okay? And NP is this segment right here. Okay? I'm not saying they're congruent because that's not given to us. That's what we're trying to prove, right? So we don't know that they're congruent yet, but that's what we're trying to get to. Does everybody see our target? Cool. So here's my game plan. What I'm going to try and do is prove these two triangles congruent, because if they're congruent, then their parts are congruent, right? And I win. So I need to get as much information about these two triangles as possible. Okay? Right now, all we have is a side, right? If we could figure out a little bit more, that would be great. Like frosted flakes. can we add to our diagram and why? Yeah, housing gay.
We have the hypotenuse of the internal triangle because of the isosceles.
So he's saying, yeah, these two are going to be congruent. And how do we know that? Because look, this is an upside down isosceles triangle. Do you see it? It's got two angles that are the same, so their opposite sides are going to be the same. Now, is that the isosceles triangle theorem or the converse of the isosceles triangle theorem? Starting with the angles, we get the sides. Converse, right? Converse starts with the angles. So we're going to say by isosceles triangle theorem converse. I need a soundboard, guys. Software has one on his phone. I should probably ask him what the app is. Look at my speakers. Amazing. Dreams. Gotta dream big. Gotta dream big. All right. So those are going to be congruent. So I'm going to write that. Ln congruent to On. It spells on. Isn't the best in geometry when stuff spells? Shut up, Jerica.
Single spaced, size 12 font.
Tell 'em, Bo.
No, it's not. It's not easy.
Bunch of whiners. All right, so now we've got two sides down. Spoilers, we're not going to get that side to prove the triangles are congruent because if we got that side, then we'd just call it a day, right? So we're going to need to get some angles here. How are we going to get some angles? How's it gay? He's on fire like Australia.
MLN.
Too soon? MLN.
And NOP would be congruent because the two given angles are they make up 90.
Yeah, exactly. Right. So he's saying if blue in the unknown makes up 90 and blue in the unknown makes up 90, then the unknowns must be the same, right? What we're doing here is angle addition postulate. The two angles add up to 90. Those two angles add up to 90. If you subtract the part that's the same, we're left with what's left over, and they must be the same. So by angle addition postulate, we'll not have to get angle addition postulate, we know that angle MLN PON PON Now the question is, do we have enough information to prove the triangle's congruent now? Oh yeah, baby, we do. Side, angle, side, right? So now we say by side, angle, side. The triangles are congruent. I'm going to write MLN, no, LMN. We'll keep it alphabetical. And then I'm going to write the other one. So angle L is made up of the blue and the green side. So if I go over here and look at the blue and the green side, I find that O is going to go with L. O. M is made up of green and unknown side. Green and unknown side makes up angle P. So M and P go together. Why are you making that face, Taylor?
Jerica's seeing pictures of me.
Jerica!
She looks like her dad.
Does she look like your dad?
A little bit.
Yikes. N is blue and unknown. Blue and unknown is also N, so N goes with N. What's your dad's name, Taylor?
Andrew.
Andrew?
Yeah.
Wow. Andy and Monica. Shout out to Andy and Monica.
Gross.
Happy anniversary. Many years more.
Not quite.
Oh, sorry. Yikes. We've all been there, am I right?
They're not divorced in 17 years. Bailey, no.
Whoa.
Oh, you thought that they were divorced? My parents are.
Shout out to Joseph and Chelsea.
Shout out to Joseph and Chelsea.
No, they're
You're better apart than you are together. Well done.
Better
Well done.
My dad and
It's
stepmom.
almost my parents' 19th
My dad and
anniversary.
stepmom have a 10-year
They're so tired of each other.
And
Two
she is,
kids.
and 2 kids. She could be my sister.
No.
That's exciting. All right. So now that the triangles are congruent, I know their parts are congruent. So if look, how she makes her money is her own business, right? So the two triangles are congruent. We've shown that. So now we know their parts are congruent, which means we can say that these two sides must be the same. How do I know they're the same? Because MN and NP, I know I wrote it backwards, I'm sorry. They're the same. It should say NP up here. I know. Nope, we're good. This is fine. It's just I wrote it incorrectly up here. And the reason for that is because it's really annoying to get letters with a bar over them. It's hard to do that in Microsoft Word. It takes extra keys. And so when I'm copying and pasting, I'll be like, oh, look, there's the letters I need. Box, copy, paste, right? I screenshot and paste. But, like, it needed to be PN. My bad. Sorry. Bye. CCP.
I don't see an NP there for you to copy.
It's, no, it was from a different thing. All right, so we know that the parts are the same. So MN, congruent to PN. We're done.
I'm actually okay.
Is everybody good with this idea? Once the triangles are congruent, you can say the parts are congruent. Which parts? Well, any parts that match up. See how M and N are in the second and third position, and P and N are in the second and third? So they must go together. You can do this for anything. So, for instance, if I wanted to prove that LO is congruent to MP, so those two top parts, LO, MP, if they are, I should be able to get it from here. Well, actually, I can't do that because I'm using the wrong triangles. How about if I wanted to prove LM and OP together? Well, LM is the first two and OP are the first two. They would be congruent. OP. All right, like a dead cat.
Hey, you know what should do for the rest of my favorite YouTuber?
No one cares. All right, so by Isosceles triangle theorem converse, we know these two sides are the same. So Nolan correctly said that, look, we have two angles that were given to us, the two blue angles, right? Which means those two opposite sides are the same. Everybody cool with that? This is always true. Two bottom angles implies two sides. So whenever you have something like this, that implies this. Nope, don't care. So that implies that. That's the converse of the isosceles triangle theorem. Then by AAP, we know these two orange angles are congruent because what's left over must be the same, right? We have 90 minus whatever this is going to get us a number, right? Pretend that's 60. What's left over? 30. Well, we know that's the same as this. So if we called that 60, we have to call this 60. 90 minus 60, what's left over? 30. Now, do we know it's 60 and 30? No. But we know whatever this is, when we subtract it from 90, it's going to leave the same thing, right? On both sides. That's angle addition postulate, okay? So now we know those are congruent. And now we have enough information to prove the triangle's congruent. Side, angle, side. So they are. And if they're congruent, then their parts are congruent. The parts we're interested in. Bam. MN, PN. How you like them apples? Feel better? Huh? You what?
I had an apple for breakfast.
What kind of apple?
I don't know.
Wow, a discerning citizen. All right. Let's look at number. Cinco.
Yeah, you like it.
I think
Take that as a no.
All right.
Why say 8?
Does everybody know what an aneurysm is?
An aneurysm?
Yes.
My grandpa had one of those.
If you sniff hard enough, you can create one. Don't do it. No, 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 no. No, all you're going to end up with is people are going to think you're addicted to Coke. Don't do that. Not even once, guys. Not even once. Scooby-Dooby-Doo. ADEB is a line, is what that's saying. So it looks like a line, and you're like, I don't know if it is. Maybe that angle is, and I don't know. It is. It is. That's what they're telling you. They're collinear points. Remember we did that at the beginning of the year, and it blew your freaking mind? Yep.
H.
Right, collinear. What does that mean?
On the same line.
On the same line. All right. So AE and DB are congruent.
I don't know why that was funny.
So AE is this little bit, ooh, and DB is the, ooh.
They overlap. You know what we should do? We should get some cool like they did that one time on that one.
It's like on the kids shows where they make the noise and like, now you do it, woo. That's right.
I think most of us didn't actually say it.
Side angle side, CCP, angle addition postulate. Side angle side, CCP, angle addition postulate.
I meant Dora.
That's the geometry.
Dora was my favorite.
I don't
like instruments.
Also, we know CDE and CED are congruent. Oh my
The only part I
god.
liked about that was Pat.
Guys, what do you think's gonna? What do you think that means?
It's isosceles.
It's going to be isosceles. Great. So don't write that down yet because we need to back that up, right? We didn't get that for free. So we want to prove ACB isosceles. Well, ACB is the whole dumb thing. So again, to fit the definition of isosceles, we need to prove these two sides the same, right? Right, or at least two sides. It could be these two sides, I guess, right? Something like that. But spoilers, it's going to be these two. So if we can get this angle and this angle congruent, then boom, we get those sides for free and we win, right? So let's get as much information about these two triangles as possible, because if they're congruent, their parts are congruent, which means those angles are the same. And if those angles are the same, then bam, opposite sides are the same. You with me? All right. So we've got some overlap, so we're probably going to be using either segment addition postulate or angle addition postulate. What do you think we're going to use here? Segment addition, because there's a segment here and a segment there that overlap. It's the segments. I know, everybody was guessing, so you shouldn't feel bad for being wrong. All right, so we're also probably going to do what Housing Gate suggested earlier, is that this is an isosceles triangle, right? So let's get that done. Let's do the isosceles part first. So if we start with the angles and we get the sides, is that the converse or the regular? By isosceles triangle theorem converse. And yes, I will take off points if you write the theorem and not the converse.
What is the difference?
What?
How do you know which is which? I don't know what the heck that is.
So isosceles triangle theorem says this, Bailey. So here's the theorem. Are you with me? The theorem says if I have two sides of a triangle that are the same, then that means the angles opposite those sides, that angle and that angle, must be the same. Now the converse is the reverse of that. Not all theorems converses are true. Not all theorems go both ways, and that's totally fine. But this one does, meaning that if you start with two angles the same, then their opposite sides must be the same. So we're using the converse here because we started with the angles, right? Thank you for asking that question. So that implies that the sides are the same. What sides? CD and CE. Boop. Great. And why did we do that? Because it got us more information about these side triangles, right? And that's what we want to prove congruent. Now, we don't have enough information to prove those side triangles congruent yet, but we're getting there. All right, so what can we do with this overlap? Follow my logic. If AD plus DE equals green, and EB plus DE equals green, if I cut out the middle, what's left over must be the same. Right? It's because these are both congruent. You can't always do that for any diagram, but you can do it when they both equal themselves, right? So this green, this all equals the same thing as this. So when you overlap, you can cut it out and get what you want. So by angle addition segment addition postulate, we can say AD and EB are the same. So let's do that. By segment addition postulate, SAP, baby. We know AD congruent to EB.
I think I need a wheelchair.
Let's do BE.
It goes through places.
All right. Everybody cool with that? Overlap, we're going to be using segment addition or angle addition pretty much, right? So now we've got two sides. If only we had an angle in between them, then we could do side angle side, right? So how do we get this angle? Is there a way to do it? How's it gay?
Linear pair theorem.
Ooh. We're going to start calling you Australia. So those two are going to be the same. Here's the logic, right? Unknown angle and orange angle add up to 180. Unknown angle and orange angle add up to 180. So the unknown angles must be the same, right? There's something like segment or angle addition postulate a little bit in there, right? But we're going to say linear pair, right? Whatever's here has to add with that to 180. Whatever's here has to add with that to 180. So they must be the same. So by linear pair theorem, LPT, angle ADC congruent to angle BDC. Does everybody see the linear pair?
Yes.
Okay. So now do we have enough information to prove the triangle's congruent? These two?
Yes.
Oh, yeah. Yes, we do. So these two triangles are going to be the same. So I'm going to write that. By side angle side, triangle ADC congruent to triangle BEC. Now the whole point of all of this was to prove that angle A and angle B are the same. Because if they are, then their opposite sides are the same. Yes?
Yes.
Right? So now we're going to use that the triangles are congruent to say their parts are congruent. In particularly the parts that we want, right? So
How did we get the bottom side?
the bottom side. So we did segment addition postulate, the pink part. So Bailey, we have overlap with the greens, right? Which means if we cut out the overlap, right, what's left over must be the same, right? Good question. Thanks for asking.
Can you go down a little?
Yes, I can. So we're going to say that angle A is congruent to angle B. And we know that because corresponding parts should be congruent, right? And if you look, A and B are corresponding. They're both in the first spot, right? So that means by CCP, angle A congruent to angle B. And then from there we're going to say, therefore, by the triangle theorem converse, or the isosceles triangle theorem converse, these sides will be the same, right here, and then fits the definition of isosceles. So, everybody cool with up to here so far? There's a little bit more. So now we know that those angles are the same. We can now say that those opposite sides are the same, right? Is that the converse or the regular? We had angles, we got sides. Converse. There is a more efficient way of doing this, and I'm sorry I didn't do it. But it's good, it gets more practice at the triangle converse. Alright, so now those two angles match, or those two sides match, so we know AC is congruent to BC. And if that's true, then isn't our triangle isosceles? So now we say by definition, triangle ACB is isosceles. Remember, when you use by definition, you're saying it fits the definition, right? Definition of isosceles means two sides are the same, and oh boy, we got it. Are you starting to feel a little bit better about this?
Your
Yeah.
notes in the way.
Okay. Can anybody think of a more efficient way of doing this? I'll give you a hint. After we got to here, we could have done something a lot quicker. Can anybody see it? Once we proved the triangle's congruent. Yeah, how's it get?
We could have said both sides are the same.
Yep, so if the parts are the same, right? Well, notice these guys are parts of those triangles, right? So can we say AC and BC are the same? Well, look, AC, BC, yep. So we could have said AC and BC are the same and cut out this step. And just done it by CCP. And then we're good. Well done. Are you starting to feel a little bit better about these? They're intimidating because there's a lot of stuff. So let's back up and go over it again. Here we go. CD and CE are the same because that's an isosceles triangle, right? Converse. You with me? Taylor,
What?
are you awake or you I need you, okay? Isosceles triangle theorem converse. Two angles, it means two sides, right? Next, SAP gets us this and this, right? Cut out the middle, you get what's left over. Next, LPT means those two angles are the same, right? The blue angles, because they add up to 180 with the orange angle. They're a linear pair, right? Two angles making up a line. Then by SAS, the triangles must be congruent. If the triangles are congruent, then their parts must match up. So by CCP, these sides are the same, right? Because CA and CB are corresponding. And then we can say, look, boom, by definition, that's an isosceles triangle. Okay? So there are no real steps here of like do step one, do step two, do step three, and you win, right? Every problem is different. But the concept is the same for every problem. What you want to do, so if you're struggling and you're feeling like you're floating in space, here's the time to listen, okay? What you want to do for these types of problems is one, identify your target. I want to prove those two sides the same so I can say this is isosceles, right? Now in order to do that, one way would be know that those two angles are the same, right? Because then I win. If those two angles are the same, those two sides are the same. Notice those two angles belong to those two triangles, so if I can prove those two triangles the same, then I get the angles, right?
Yes.
Well, how do I prove the two triangles the same? Well, I get as much information about it as possible, right? So step 1, identify your target. Step 2, figure out which triangles you need to prove congruent to get that answer, right? Get as much information as possible until you can prove them congruent, and then use CCP to prove their parts congruent. So again, get your target, gather information, prove triangles congruent. Since they're congruent, you can use their parts. That's the concept for each and every one of these. Take a look at number 6. It says CA congruent CB. Let's get that done. CA, CB. That's these two sides. Ooh, what kind of triangle are we dealing with? Isosceles, which means angle A and angle B are going to be the same, right? So that's exciting. We'll get that eventually. D and F are midpoints of CA and DB. So we have midpoints here, right? And now, normally, if that's a midpoint of this segment, we'd have to use different tick marks, right? But since both sides are the same, don't we know that these will be the same as well? Okay, so we can use the same tick marks here and here. DE bisects AG. Bisects means to cut in half. Bi means two, sect means cut, right? Like sectum sempra. No? Hepler Prince? Okay.
Oh. What?
Hannah, without you, where would I be?
I don't remember what that one is.
DE bisects AG.
What's that one?
No.
Yeah, that.
And then FG bisects EB.
All I know is
Bad ones.
We are trying to prove that DE is FG. Well, DE is this, and FG is that. So we don't know they're congruent yet. We're going to try and prove that. That's our target. So what triangles do you think we need to prove congruent to accomplish this?
I don't get how you need to alter the bottom parts of it.
Great question. So DE bisects AG, right? So it cuts that into two equal pieces. We good with that? Okay. FG is bisected by EB, or bisects EB. So this cuts these two in half. Well, if that's already a 2, and this is cut in half, then this must be a 2 as well. You follow me now? Great question. Great question. I'll say it again. This guy gets cut in half, right? Here. And then it says this guy's cut in half. Well, if that's already a 2, then that has to be a 2 as well, right? Yeah, exactly. So, which triangles am I going to have to prove congruent so I can say that those two red lines are congruent? Which triangles? The two left and right ones, right? ADE and GFH, right? Or GFE. Those are the two I need to prove congruent. Now, do I have enough information to prove them congruent right off the bat? No, but I have two sides. If only I could get some more information. Try this one on your own. You need, yeah, at least an angle, right? Because if you, right, because the logic is like, well, you could do side, 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 but if you had side, 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 you'd already, you'd win. You know what I mean? Right? So we're not going to get that side. We're going to get that after we prove it congruent. So we need to find an angle somewhere. Work together.
See, like, I think I know what I'm doing if
This is
I do it by
homework.
myself.
Try it.
You said that
No,
we could skip
try.
it.
I'm trying.
Look at what we have and see if you can get that last angle. You can do this. You can.
You said that.
Look at me. Look at me. I know you can. It's going to take a little while, but you got to try it. Relax and look at the information that was given to you. Don't forget to look at the big picture. Work together. I know you can do this. I mean, I'm not just saying that to say that.
So we could skip that. You know when we do like side times side, you can skip one part and you can skip the angle part.
One part max. No. Skip one part means. So a lot of people ask me, like, let's do this. Let's say, why isn't this side angle side? And the reason for that is to get from side to angle, that's fine, we can skip anything, right? But to get from this angle to this side, I skip a side and an angle. I skip two things, can't do that, okay?
Yeah, but not when we would only be skipping one. Sure. If we went side, side, side.
Yes, side, side, side will work, but here's why I know we're not going to end up using it, okay? Because if I knew that this side and this side were the same, then the problem would be done, right?
But we do know.
We don't, not yet, it says prove it. I colored it to show you the target, I didn't mark it. Does that make sense? Okay.
So why can't we use
You can use side, side, side. I know we're not going to use it though, because if we were able to use side, 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 I wouldn't need to prove the triangle's congruent because I already win.
That side is congruent.
Right? No, Jericho, look at me. Don't listen to them. Okay, I've got you. You just stay with me. If I knew these sides were congruent, yeah, I could prove that the triangle is congruent. But why would I want to do that? Because I'd already won by then.
But then that's the point.
Right, yes. So, if for some reason you were able to say, oh look, these are congruent, great, you're done. You would never end up using side, side, side because the proof would end before you were done, right? The proof would end before you use side, side, side.
I think what she's saying is that then why don't we just find that side, because that would make it easier.
It would, yes, but to find it, we're going to have to prove those two triangles congruent. So it's a what comes first situation. You're going to have to prove the triangles congruent in order to get the side, right? If you were able to get the side, great. But the only way to do it is to get the triangles first, okay? So we're going to not end up using side, side, side. We need one of the angles. All right, I'll come around and help. Please work on this on your own, and this for homework. Okay, now is it converse or regular? Exactly, good job. Now,
I'm thinking of SAP. Where's SAP?
Shelby, I'm on my way. What?
I did that, because then.
Ooh, new strategy. Good job.
But I don't actually know if those
I don't know.
So it turns out that that angle, the red and that black one are actually the same.
I see it, but how do I know that?
Okay, here's the problem. We don't know that those two are the same. We don't know anything about those angles, so we can't use these. See what I'm saying? We don't know anything about either of these angles, so that angle could be different than that one, right?
We have written stuff already.
Oh.
Stuff we put down.
I don't know what you mean. No, that would, all the stuff I have on there was given. Okay? Alright, yes.
Should I do this half?
Yes, that's great. And then we can use this. Yes, excellent. Right, now that the triangle's congruent, we can prove the parts congruent. Now it's time to use CCP. Okay? Yes.
Sure.
Ask her,
I have a question.
because she's your partner right now, right? You guys partner or not? Okay.
What is this?
What mean?
SAP.
SAP, segment addition postulate. So we were able to say that this right here is congruent to that, because that was given to us. Okay? So those two lines. So if we cut out the middle, what's left over are those guys? That's segment addition postulate. That's this thing, Calvin? If I know these are both equal, if I cut out this, what's left over must be equal, right? That's the idea there. Okay. So you forgot to mark your diagram saying that those things were congruent. The big pieces, AE, and
I have one
you
thing.
forgot to mark that and that is congruent. So the way we do that is with the squiggle, right?
Yeah.
I'll be there in a second.
Is this right? Did I do that?
Yes, you got it. You saw it.
So then do you do like this and that?
Yeah. So the only thing you're missing is by that theorem, you know A and B are the same, right? That's what you need to write.
Okay.
And then by now you can say by SAS they're congruent. And now corresponding parts. Yeah.
Well, Taylor kind of helped.
I know, but that's the point. Right now you should do it 100% on your own. Yes.
So if I go back, I saw this triangle, angle, I get that.
So these two sides are this is different. These two sides are see how they have the same difference. And they're that's what this means. This wiggle. That means this whole side and this whole side is the same, which means they're opposite angles. Okay? So by isosceles triangle here, those two angles are the same. And it's because